maybe we can get started. It's a pleasure to welcome Professor Hofmann from the Max Planck Institute for Nuclear Physics in Heidelberg. In fact, we have been lucky that he made it in time. His flight had 2 hours delay, so he just came 5 minutes ago. Professor Hofmann has been, as many of the high-energy astrophysicists, been working with accelerator-based particle physics before. He was, I think, the spokesperson of what's called the TPC experiment.
For TPC, yeah.
And he was also the chairman of the collaboration board of TRB and LHCb. And so he worked with both SLAC and CERN and DC. And now he's the spokesperson for the HESS experiment, which most of you probably know. Got the CART prize in 2006. And this will be the subject of his talk. We'll be talking about HESS and the configuration of HESS with the CTA. Thanks. Please.
Yeah, thanks a lot. What I would like to do is tell you a little bit about very high energy gamma ray astronomy, very high energy meaning tera-electron volts, which is pretty much a new regime to astronomy. We have, since just a couple of years, it's for the first time that we have maps, real maps of the sky at tera-electron volt energies. What you see here is the band of the Milky Way as it looks in the optical and as it looks in very high energy gamma rays. And clearly it's a fairly distinct appearance in very high energy gamma rays. The Milky Way is lined with a number of sources, mostly extended. And as we zoom along the Milky Way, we see that this basically continues all along our galaxy. And what I want to do in this talk is first just motivate a little bit why we are doing that, then tell you how the instruments which we're using, these Cherenkov telescopes, work, then give you a tour of some of the things which we've seen in the galaxy, and then finally talk a little bit about the next big step forward, the next big instrument which we're planning right now, which is CTA. So let me start with a very brief motivation. There are two kinds of motivation. One is sort of rather generic, which is that radiation which reaches us from the cosmos covers about 70 octaves in frequency space. And of course, to understand really what's going on in the cosmos, what we've learned in the last century, that basically you need to cover all these wavelengths. And the galaxy, as you see here, looks rather different in the different wavelengths. I sometimes like to illustrate this. You can imagine the radiation coming from space as a 50-meter long piano. And basically what we're going to do is explore the very right-hand keys of this piano. Okay, so this is the Milky Way as it looks in radio, for example, in infrared, in visible light. And you see it really has a rather distinct appearance, different appearance. In X-rays, one has a rather short range. It sees mostly local structures. In gamma rays in the equal energy range, the band of the Milky Way is rather clearly visible, but most of it is sort of diffuse emission spread out along the Milky Way. And what we want to do now is just ask, how does the sky look at even higher energies? And so what we want to do is move up another 3 orders of magnitude in energy to tera-electron volt gamma rays. And basically, a couple of years ago, the sky at these energies was essentially empty. This is a picture of the tera-electron volt sky as it was seen in 1999, the northern sky, the southern sky. Basically, many parts of the sky had never been looked at, and there were a handful of objects known to emit tera-electron volt gamma rays. The field, this down here just shows a zoom into the band of the galaxy. The field progressed slowly, number of sources growing a little bit in 2001, 2003. Then at that time, our HESS experiment turned on. The objects discovered with HESS are labeled in yellow. And you see that now the sky starts to fill up. This is 2007. And for the first time, we have actually not really covered the full sky, but covered, at least surveyed the band of the Milky Way. And this is the view of the Milky Way as I've shown you before. In 4 bands of galactic longitude from roughly 60 degrees to roughly minus 80 degrees longitude. The various sources here are labeled with the HESS-J and then the coordinates. which means that essentially all of these sources were discovered by Hess. And what you notice, they line the band of the galaxy, meaning they are fairly far away. And you also notice that most of them are not just points in the sky, they're sort of extended in complex structures. So this is the one motivation, is just that there's a new sky out there to be explored and new things to be learned. There's, however, a rather concrete goal behind this research, and this is searching for the origin of high-energy cosmic rays. As you probably know, we believe that cosmic rays are accelerated in supernova acceleration. A nucleus sort of rides the supernova shock wave as it explodes, as it moves at a few percent of speed of light into interstellar space, and particles are accelerated to very high energy. So I'll say a little bit more in a second. Now the problem is that these charged nuclei accelerated presumably in supernovae, which make up our cosmic rays, are then deflected in interstellar magnetic fields, and they don't reach the Earth from the direction in which they're produced, but rather arrive sort of randomized, uniformly distributed over the sky, and a typical PeV particle doesn't make it on a straight track from the nearest star to Earth. So one cannot use the cosmic rays themselves to study the accelerators of cosmic rays. But what happens is that once in a while, a proton, which is accelerated, collides with a gas nucleus, makes pions, and the pions decay and make gamma rays and neutrinos. And of course, the gamma rays and also neutrinos propagate on straight paths to Earth, and they can be used to image cosmic accelerators. So the idea is basically to use gamma ray astronomy and hopefully at some point neutrino astronomy to image cosmic particle accelerators in sort of via these secondary reactions. And basically at this point we know that there are about 70 of these cosmic accelerators out there in space which accelerate particles to TeV or even hundreds of TeV and beyond. Actually, supernova remnants are only a small fraction of them. There are pulsar nebula, about a little over a dozen, close to 2 dozen sources where we don't know what they are. They're binary systems, they're active galactic nuclei. And this little diagram down here shows you just once more how, in recent years, the number of objects detected at these energies has increased, and the contribution of our experiment. So let me tell you very briefly how these things work. Basically, at tera-electron volt energies, gamma rays don't reach the ground. They interact roughly at 10 kilometers height in the atmosphere, 10 to 20 kilometers. They generate a cascade of secondary particles, electrons and positrons. These in turn again don't reach the ground, but they emit Cherenkov light in the atmosphere. It's a forward bluish beamed light which illuminates a 120-meter radius, roughly circle on the ground. And now the idea is to just place a telescope on the ground and image the gamma ray or the air shower using this Cherenkov light. And the big advantage one has is that one has a huge detection area. Basically, the telescope can be somewhere in the light pool, which is of the order of 10 to the 5 square meters, which makes it very easy to catch rare gamma rays, whereas satellite instruments with sort of square meter detection area simply run out of counting rate at energies of a couple of GeV or maybe some tens of GeV. So the only way right now to get high sensitivity at tera-electron volt energies are these ground-based instruments which use the atmosphere as detector medium. You can imagine that in a very simplistic way that these gamma rays entering the atmosphere look a little bit like meteors. They leave a light trail in the atmosphere, and what our telescopes do is from different sides they take pictures. There are 4 telescopes. They take from different views pictures of these trails in the atmosphere, and then they're reconstructed. Of course, the trails are much fainter than meteor trails, and they're also much faster. The whole thing is over in a couple of nanoseconds. But again, like for a meteor shower, if you simply superimpose pictures, you immediately see where the source in the sky is. And gamma ray showers would look rather similar, with the exception that with our instruments, we get a fairly coarse picture of these showers, but it is sufficient enough to sort of reconstruct the direction from which these rays are coming. So that was very briefly the detection principle. It is not new. It was first used in 1953, where people put a photomultiplier and a mirror into a garbage can and looked at the sky, and they saw pulses. They published it in Nature. I think right now we've tried to repeat this. You see all kinds of pulses. They're probably not cosmic rays. But anyway, Then, after World War II, there were lots of searchlights left, which allowed people to do coincidence techniques and do that on a bit more professional status. But really, the breakthrough came with the American Whipple instrument, which was inaugurated here in 1968. But then essentially it took 20 years until the first high-energy gamma ray source was discovered, which was the Crab Nebula. And it took them 50 hours to get a significant signal. Just once more to illustrate progress, the HESS telescopes look rather similar. There are 4 of these telescopes in Namibia. But they can basically detect a Crab-like source in 30 seconds rather than 50 hours. And they have a sensitivity which goes down into the percent Crab regime. And sort of the next big step will be to go to millicrabs in sensitivity. Okay, that just illustrates it's really a big collaboration of German, French, UK, Irish, and a number of other institutes. A group of about 150 people running the experiment. A key feature is the location. In Namibia, we went to the southern hemisphere because there you see the band of the Milky Way across the sky, and many of the interesting objects you want to look at are in the Milky Way, which is why you ideally want to be in the southern hemisphere. Another key feature is a relatively large field of view of these instruments. These are the photon detection system, we call them cameras. They're basically bundles of 960 photomultipliers, and they cover a 5-degree field of view, about 10 times the size of the moon, which allows for surveys not of the full sky, but at least of limited regions of the sky. And this box also contains, which is novel in this field, the complete electronics. Okay, this is a picture of one of the telescopes. 100 square meter area needed to collect the faint Cherenkov light. One can only observe in moonless nights, giving you about 1,000 hours per year. 5 to 10 objects are tracked across the sky, and then air showers are recorded at about 300 hertz. Most of them are just cosmic ray showers. Only a few of them are the interesting gamma ray showers. And the stuff is analyzed online in Namibia, but then the final analysis is done in Europe. Okay, just to illustrate the precision which is now reached with these instruments, this blinking thing here is the galactic center. There's one source right at the galactic center, and the interesting issues are the blinking object here is Sagittarius A star, the supermassive black hole at the galactic center, and we've meanwhile succeeded to localize this gamma ray source at the galactic center to within essentially 10 arc seconds from the galactic center, excluding, for example, Sagittarius A East, the nearby supernova remnant, as a source, and making it very likely that it's an object right very close to the black hole. Now, I won't talk much about the galactic center. I think you have sort of the world experts in dark matter here. For a long time there was a discussion, could this be dark matter annihilating? But I think right now we have concluded from the spectral properties of this source that it is just, in quotes, an astrophysical particle accelerator, and unfortunately it's not the dark matter acceleration annihilation, which a lot of us would like to see. Rather, I would like to concentrate on a number of other objects and try to explain what we see and give you a little bit of a glimpse of the physics behind these objects. Now let me start. These are the 4 kinds of objects I'll discuss: supernova remnants, pulsar nebula, binary systems, and the so-called dark sources. So let's first look at supernova remnants. We have, for the first time, really seen resolved shells of remnants. This is RxJ 1713, where you see in TV gamma rays a shell glowing with a diameter of about 1 degree. And this, for the first time, unambiguously demonstrates that there are high-energy particles, multi-TeV particles, produced in the shells of supernova remnants. So it's no question that supernova are very high-energy cosmic particle accelerators. It's not the only one. There are even RxJ 0852, called also Vila Junior, is sort of a 2-degree diameter shell. And again, here it's very helpful to have a large field of view, allowing to really image these objects. We can look at the energy spectrum, in this case of the first remnant I showed. The energy spectrum here shown on a log-log plot, the rate of gamma rays as a function of energy. It follows a straight line on this log-log plot, which has a slope of -2, meaning it falls like a power law e to the -2. And then at energies of some tens of tera-electron volts, there seems to be a break, which seems to indicate that this cosmic accelerator is slowly running out of steam at energies around 100 TeV or so. But it clearly demonstrates that the supernova shell accelerates particles to 100 TeV and beyond. Remember, these gamma rays are secondary particles produced in reactions. Now, let me very briefly illustrate or discuss whether this is what we expect and whether we can understand that. And let me just remind you how these cosmic accelerators are believed to work. In fact, they're not so dissimilar from the man-made accelerators we know. In a man-made accelerator, a magnetic field serves to keep a particle on a circular orbit, and then the particle is kicked periodically by electric fields, and extracting it after a certain while will get some more energetic beam. Now, the cosmic particle accelerators use pretty much the same ideas. They use magnetic fields to keep particles in acceleration regions, and they kick it periodically. So, globally it's similar. The details are a little bit different. What we have here is a particle meandering in magnetic fields, but these are sort of random interstellar magnetic fields in the vicinity of the supernova. So it's undergoing kind of a Brownian motion. And what's illustrated here is the supernova shock wave, which is a plasma shock wave coming at a few percent of the speed of light. Now, the plasma shock wave overruns the particle, which suddenly finds itself in a moving medium, and of course then is accelerated to the speed of the medium as it interacts with the local magnetic fields. Now, normally that would be it. But now the particle in this Brownian motion can again go ahead of the shock wave, being kicked a second time, maybe being kicked a third time, a fourth time, and so on. So most of the particles are kicked just once. Very few particles are kicked very often. As a result, these cosmic accelerators generate an energy spectrum with lots of low energy particles and few high energy particles. This mechanism was invented long ago by Enrico Fermi. Now let me just give you a few details. Basically, a cycle, typically a synchrotron radius is almost light years. So a cycle across the shock waves takes years, and the particle gains a few percent of energy because that's the speed of the shock wave. So this is a very slow process. It takes hundreds of thousands of years. It naturally turns out to generate a power law spectrum e to the minus 2, because there's a certain probability at each step that the particle drops behind the shock wave. And that naturally gives power law spectra. The exact index depends a little bit on the strength of the shock wave, so there's a little correction, but essentially it's close to 2. It also predicts that there's a peak energy which one can reach in these accelerators, which are determined on the one hand by the size, by the age of the accelerator, because it's such a slow process. A young accelerator cannot make very high energy particles, and by the fact that, of course, at some point the gyro radius gets bigger than the system and then the particle escapes. And so typically, there's of the order of 10 to the 15 electron volt, depending on the exact size of the shock wave peak energy, which sort of explains why these accelerators run out at a couple of hundred TeV in gamma rays. It is a process which is predicted to have an amazing efficiency, converting up to half of the kinetic energy of the shock wave into energy of high energy particles. So basically, this e to the minus 2 power law spectrum observed for gamma rays, which cuts off at a few hundred TeV, is what we expect for this classical Fermi acceleration process. There are, however, a few things which we don't understand, and one of the things which we don't understand is the correlation between the TeV gamma rays, which are shown here in color, and the X-rays, which are shown as contours. And you see that this object is an X-ray source, and the X-rays trace pretty much the gamma rays. They peak in the same places, they show the same contours. Now, why is it surprising that a supernova emits X-rays and gamma rays with the same morphology and the same structure? Well, let's return for a moment to the wideband spectra over the very wide energy range. Plot here the energy flux per decade of the spectrum, and look what different primary accelerated particles generate in terms of radiation. We can first consider a cosmic electron accelerator, something which accelerates electrons to high energies. Now, what electrons can do is they can do synchrotron radiation, so one gets a synchrotron radiation bump. Synchrotron radiation essentially is the electrons scattering off virtual quanta in the magnetic field and emitting them as real quanta. It's kind of a Compton scattering process of virtual quanta. Now the same Compton scattering, of course, the electrons can do with real photons, like microwave background photons or infrared visible light. This is called inverse Compton scattering, and the electron can transfer a significant fraction of its energy to a gamma ray, which then emerges as a TV gamma ray. So electron accelerators generate this characteristic double-humped frequency spectra, radiation spectra, one peak due to synchrotron radiation, one peak due to inverse Compton upscattering. And by changing the magnetic field, increasing the magnetic field increases the amount of synchrotron radiation. So for an electron accelerator, it's perfectly normal to have high-energy gamma rays and synchrotron radiation correlated. For a proton accelerator, on the other hand, a proton accelerator makes gamma rays by pi naught production on gas. And there's no reason why this process does not generate any X-rays, and there's no reason why it should be correlated with X-rays. Now, however, we do believe that supernova remnants are cosmic proton accelerators. So the question is then, why is this surprising correlation between X-rays and gamma rays there? This is a cosmic ray nuclear accelerator. Well, there's quite a debate going on in the community. There's essentially two schools. One school says, well, this thing does not accelerate nuclei at all. It just accelerates electrons, and therefore makes the X-rays and the gamma rays, and one needs a magnetic field of about 10 microgauss to get the relative rates right. The other school says, well, the thing is really a cosmic proton accelerator. It accelerates protons and very few electrons. These very few electrons cannot make gamma rays because they're just too few to upscatter. However, if I combine it with a high magnetic field, they can generate the X-rays. So in this school, the few electrons generate the X-rays in a high magnetic field, and the protons in the gas generate the gamma rays. But then why should the two be correlated? Well, it turns out there is a speculative mechanism which goes as follows. As protons are accelerated in the gas, they excite magnetic field turbulences. And it turns out that the strength of the magnetic field squared, the magnetic field energy, is proportional to the number of cosmic rays accelerated. So the cosmic rays which are accelerated generate a magnetic field, and in this magnetic field the electrons then radiate and generate X-rays. And with that mechanism, if it's really true, one indeed does get a correlation between proton-produced gamma rays and X-rays, if indeed magnetic fields are high. So one of the key issues is, are magnetic fields in supernova relatively low, a couple of microgaussish, or are they high to allow this mechanism to work? Again, this is a much debated question. There has been some rather interesting X-ray data recently. This is a section of this remnant which I just showed you. This is also a section emitting lots of TV gamma rays. But now this is an X-ray image in different years. And what you notice is that this X-ray image, these are just two little squares out of the big image, this X-ray image changes over years. Now X-rays come from electrons. If the X-ray image changes over years, it means the electron population changes. However, the only way electron populations can change is if you accelerate new electrons or the electrons die away by radiative losses. In order to make them die away on timescales of years by radiative losses, one needs fairly high magnetic fields. In fact, fields in the milligauss region. So the fact that the X-ray image can change on a timescale of years means short cooling timescales, high magnetic fields, arguing that this mixed scenario could indeed be the right one. However, of course, there's still a remaining question whether the high fields, which are presumably here and here in this remnant, are characteristic for the entire remnant or whether they are sort of special locations. So this is something which is much under debate in order to solve this issue, whether supernova indeed accelerate cosmic nuclei to high energies, or whether there's sources of cosmic rays, and how and when particles are exactly released. One is now trying to go a different route, namely looking at supernova remnants, like this cartoon here, which interact with molecular clouds, which high density regions, or which have high density regions nearby, because then if you find gamma rays from this high density region, it clearly means one has accelerated nuclei which interact with the gas, which is there. Electrons cannot do that. And even nicer is if one has clouds which are a distance away from the remnant, because that allows to study how the protons propagate are accelerated in the remnant, then propagate and interact out here with gas clouds ideally located at different distances. Now again, in just the last year, we have for the first time seen some systems which are relevant for that. One is this is a radio and infrared picture of a remnant called W28. This is the shell here in radio. And there's some nearby H2 regions which represent dense gas clouds. Again, looking at this thing in TV gamma rays, one finds interestingly that there's TV gamma rays produced exactly in the regions where the supernova shockwave interacts with the gas cloud, and in the two regions where we believe there are big gas clouds fairly nearby the remnant. Now, this is an old remnant, it's about 100 kiloyears old, so probably it's already sort of running out of steam and it's slowly spreading its cosmic rays into the ambient media. Of course, there's still some question of to be resolved whether these is not a chance coincidence of sources which are actually in the background or in the foreground. The problem with these sky images is always you can only say they're close by in projection, whether they're really close by in space is an issue which is a bit difficult to resolve. But these are, I think, now interesting hints coming and showing that supernova indeed accelerate cosmic rays, nuclear cosmic rays. Now let me just move on to the next object, which are pulsar nebula. This is the Vela region. Here you see this Vela Junior supernova remnant glowing gamma rays. Here's the Vela pulsar, and from this Vela pulsar is emerging kind of a flow, a stream of gamma rays, or a stream of high energy particles. What this is believed to be is a pulsar wind nebula. What you see here is a particularly nice pulsar wind nebula, a nice spherical one in X-rays. This is a supernova shell. Inside the shell is a pulsar. The pulsar is a rotating neutron star which accelerates a steady stream of electrons and positrons. And these electrons and positrons, high energy, blow a bubble inside the supernova remnant, which is filled with high energy electrons, positrons, which are then highly visible in X-rays, and which of course also should make, by this inverse upscattering, high energy gamma rays. Now, a puzzling thing is why the natural kind of pulsar wind nebula is something spherical surrounding a pulsar. The strange thing is that this is not what we see, at least not what we see here. What we see is the pulsar here, and then a stream of high energy particles generating gamma rays down here. This, interestingly enough, this source has its peak energy output at about 10 teraelectron volt. So this is where it outputs most of its energy. Now, one could argue maybe this Vela pulsar is known to have a kind of jet. Maybe this is a sort of a continuation of the jet of the pulsar spin axis. But if one looks in X-ray images, one notices that the alignment of the pulsar axis is not the alignment in which the high energy particle seems to move. So what's going on there? It's an interesting question. Is this an exotic candidate? It is surprisingly not. What we see is we see now almost 24 of these pulsar wind nebula. You see here by the blinking symbol, it's always indicated the location of the pulsar, and the color gives you the high energy gamma rays which sort of trace high energy electrons propagating away from the pulsar. And always, these are big sources. They are typically sort of 10 parsecs, 30 light years across, and they're all displaced from the pulsar by a significant amount. How can that be? Well, it's a good question. We're still trying to find the answer. One explanation is that in a supernova explosion, the pulsar typically gets a kick. It can move with speeds of a few hundred kilometers per second, and it can now happen that the pulsar sort of just, with this pulsar wind nebula, this shell filled of electrons, moves through the supernova remnant, the explosion shock wave which stays in place, and after some kiloyears, the pulsar penetrates the supernova explosion shock wave, and this pulsar wind nebula is sort of stripped and is trailing behind the pulsar. So that would generate the morphology which we're seeing. Unfortunately, it turns out it's the wrong explanation, because in particular in case of the Vela pulsar, we know in which direction the Vela pulsar is moving, and it's moving in the wrong direction. So what else could it be? Well, one could of course need to ask, is it maybe a chance coincidence that there's a pulsar and the gamma ray source has nothing at all to do with the pulsar? Well, Fortunately, at least in one case, we could look at this in a bit more detail. In this puzzle, what we could do here is we had this is a strong enough source that we can plot the distribution of high energy gamma rays in blue, medium energy gamma rays in green, low energy gamma rays in red. And what you see is the high energy gamma rays seem to come from the vicinity of the pulsar. The green ones are already further away. The red, the low energy gamma rays, low meaning still TeV, are spread out over a degree in space. Now this is quite natural if you assume that you have an electron source here, because the electrons from the pulsar move away, they move in magnetic fields, they emit synchrotron radiation, they lose energy. So the further away from the pulsar they are, the lower the energy is and the lower is the energy of the gamma rays. So this clearly shows that whatever is making this radiation comes from somewhere this region here and reduces drastically the probability for a chance coincidence. Now again, interesting enough, recently, just last year, the direction of motion of this pulsar has been measured and it's moving in this direction here. So again, it's the wrong direction. Now what could it be? There's one possible other explanation. This is supernova going off in an inhomogeneous medium. This is a simulation, MHD simulation of an explosion at different years. And what's happening is that the supernova exploding in a dense medium here and a thin medium here. And then there's a reverse shock, the shock wave, the explosion wave sort of bouncing back from the dense medium and shifting the entire interior of this remnant, including the pulsar nebula, to the side. So the pulsar stays put where it is, but the entire electron-positron bubble is sort of by the ambient pressure shifted in one direction. If one waits for a long time, then it would be the reverse shock from this side would come and the thing would be shifted back. Now understanding that, understanding how these bubbles evolve and how they interact is a very interesting issue in plasma physics. And again, I think we're certainly not sure whether this is the right explanation, but it looks like one. Another very interesting object we came across, this is the same field of view of the pulsar and the pulsar nebula, which I discussed, is this fellow down here, LS5439, which is one of the very few point-like sources in the galaxy which are not extended. But this is a sort of a steady state. If we were to plot it time resolved, we'd see that this thing blinks in gamma rays at a rate of about the frequency of about 4 days. That brings me to the next subject, which is a particularly interesting object class, which are binary systems, where one has a binary, like a neutron star made of a neutron star or black hole, which is accreting mass from a massive companion. And right now, we know 4 of these binary systems. I want to concentrate on LS5039, which is, it's not quite clear whether it's a black hole or a pulsar, in a very narrow 4-day orbit, elliptical orbit, around a very massive star. Now what's very interesting is, I mean, the problem one has with gamma rays, with high energy astrophysics is, this is not laboratory work. You cannot sort of change accelerator parameters to see how it reacts to change ambient conditions. But here, what you have is you have presumably a particle accelerator which is changing, which is moving in an ambient changing field. It's experiencing varying magnetic fields, varying radiation flows from this star here. And so here one can really study how a cosmic particle accelerator reacts to variant ambient conditions. And it reacts in an interesting way. It produces this essentially sinusoidal modulation. At first glance, one would assume that most of the action is when the black hole and the massive star close to each other, because then they're most interacting, obviously, most violently. It's not the case. The highest gamma ray flux comes in the front part of the orbit. The observer is here, whereas the minimum is in the rear part of the orbit. Now, it is actually a complicated mix of effects, but the dominant one is simply pair production. When the gamma ray source, or the cosmic accelerator, is behind this massive star, then the gamma rays and the stellar photons collide head-on, and they have high enough energies to pair-produce electron-positron pairs. And the flux of photons from the star is so big that essentially 100% of the gamma rays produced in the back are absorbed. Whereas in the front, they move in parallel and they don't change, they don't cross the pair production threshold. So this is sort of the dominant effect, but then come various other effects like increased cooling in this region. So the fact that also the energy spectra of the accelerated particle change as the source goes around in this orbit allows us to really learn a lot about the detailed mechanics, how this machine works. A particularly interesting object are so-called dark sources. This is something discovered first a couple of years ago. Dark sources are things you see gamma rays from a region of the sky, you look there with X-ray instruments or radio telescopes and you see essentially nothing, which looks suspicious. Now, this is not a rare phenomenon. There are about 8 or 10 or even more of these dark sources. And now the question is, what are these guys? They are objects which one sees or discovers only in very high energy gamma rays. There are various possibilities. It could be an entirely new class of objects. It could be the real sources of cosmic rays, because purely hadronic accelerators would not generate X-rays or radio rays. They would only make gamma rays. Of course, it could be that the instruments which we looked at are simply not sensitive enough in X-rays to see what's going on there, or nobody has bothered to look deep enough. Now, it turns out the truth probably is a mix of all of these things. In some of the objects, I should just mention, so there are various ideas which are partly rather exotic, like this could be remnants of gamma ray bursts which went off in the Milky Way in their giant magnetic field, cooling all the electrons to very low energies and leaving only protons left over. Or generally old objects where the electrons are gone and we have only high energy neutrons. Or of course it could possibly some kind of dark matter halo objects and emitting mass black holes, and you name it. Now it turns out, at least in some cases, if one looks more closely, these dark objects don't remain dark. The yellow circles show you the size and location of the TV gamma ray source, and at least in these two cases, after we looked with XMM in a deeper exposure, we found that inside the TV gamma ray source, there's an extended X-ray source, which presumably is, again, one of these pulsar nebula. So inside this X-ray source, presumably is a pulsar which generates electrons, and they make the X-rays and the TV gamma rays. And it's just that so far, the X-ray exposures were not sensitive enough to detect these sources. And it's interesting that for sources which are bigger than a few arc minutes, Cherenkov telescopes are now more sensitive than X-ray instruments. Another example was just published recently. This was the source SJ1731-347, where people in radio images found at the location of the main source, it's probably a double source, something resembling a supernova shell. So in some of these cases, looking more deeply, it turns out you see things which you wouldn't have seen otherwise, because just the signal to noise in this radio image would not be good enough to alone claim this as a supernova shell. But since you know that there are energy gamma rays, this makes it a rather reliable association. On the other hand, one has looked deeply on some of the other of these sources, spending a lot of X-ray time on it, and there's nothing in this location of the sky. So there seem to be different classes of sources. The one class is where one just hasn't been sensitive enough. But there seems to be really a new class which emit only TV gamma rays, but very little else, at least not a rate detectable with current instruments, which is quite interesting. Let me just touch briefly. I've so far concentrated on what we see in our galaxy. Of course, if you've seen from the maps initially, there are also a number of extragalactic sources, about 20 of them, most of them, essentially all of them, associated with active galactic nuclei, where a supermassive black hole in the center of a galaxy accretes matter, and a jet of a high-energy jet, plasma jet, is generated. And this jet is typically in these objects pointing towards us. Now, what is interesting is the properties which we measure. This shows a light curve detected for one of these active galaxies, PKS 2155, at a redshift of about 0.1, so it's still a reasonably close by source. And what you see here is the rate of gamma rays plotted in 2-minute bins, and you see that the thing varies on time scales of minutes. There are very rapid variations of the gamma ray flux. Now, why is that interesting and exciting? Well, The one thing is, the source has a strength which is 15 times brighter than the brightest source in our galaxy, which is the Crab Nebula. However, it is much further away, and it means that in terms of equivalent luminosity, it is about 10 to the 12 times brighter than the Crab Nebula. It manages to turn on and off this luminosity in a matter of a minute. What's particularly surprising is one can look at the light crossing time of the supermassive black hole at the core of the galaxy. The light crossing time of the supermassive black hole is a couple of hours. So light takes a couple of hours to cross the radius of the black hole, yet the thing managed to vary its intensity on minute time scales, which usually only works if one has a highly relativistic jet where Doppler boosting effects increase the perceived rate of variation. But then one would need Doppler factors of 100, and at least nobody right now knows how to make these Doppler factors or to make these jets go at such a high speed. Another interesting application is that one can search for violation of Lorentz invariance and indication of quantum gravity. Because these are very high energy gamma rays propagating over megaparsec. They have very short wavelengths. And the prediction is that, for example, if quantum gravity introduces a kind of foamy space-time structure on very small scales, then these gamma rays have a short enough wavelengths that over the tremendous distances, this could give a noticeable effect on propagation speeds. Which would mean that if one looks at different energies, that these peaks depend slightly on the energy of gamma rays. Now, we've looked for that, and there's no significant effect. But what is interesting is that if one uses models which relate the variation in speed of propagation to essentially the energy of the gamma rays divided by a characteristic mass scale of quantum gravity, one finds that one can constrain the mass scale of quantum gravity to be more than about 4% of the Planck mass. Meaning, one is really testing with these high energy gamma rays space-time, at least in certain models, on scales approaching the Planck mass. And the idea is that with the next generation of instruments, one will go from a few percent to actually to the Planck mass itself. So, where are we now? Well, basically, I think there has been a major breakthrough over the last years, in the sense that we're now doing real astronomy at these very high energies. We're producing light curves, we're producing real sky maps. We're starting to find some of the pieces of the puzzle, but we still have lots of questions left over and lots of things which we don't understand. And that brings me to the final point which I want to cover, which is the next big step which we're now trying to get going, which is called CTA, the Cherenkov Telescope Array, which is an instrument which takes us another order of magnitude beyond what we've now in capabilities. And this is sort of a simulation of a typical CTA field of view. So rather than seeing a supernova once in a while, you have lots of them in a single field of view. And that's of course important because all of these objects are different. Now you have enough of them to do population studies and to really look what's characteristic and what's sort of a specific feature of individual objects. There's a wide range of physics issues concerning both specific source types from supernova remnants to gamma ray bursts. And there's a range of sort of generic questions like searching for the origin of cosmic rays, searching for signatures of annihilating dark matter, testing, like I've just outlined, space-time and relativity, and one can actually do quite a bit of cosmology with such an instrument. I don't have the time to go into details. Let me just give you a wish list which we've come up with, what we want to get from a next generation instrument. We'd like to roughly have 10 times more sensitivity, to just get more sources, to look deeper through the entire galaxy, essentially. We'd like to have a lower energy threshold, because with a lower energy threshold you can look deeper into the universe, and you can probe, for example, dark matter on lower mass scales. At the same time, we'd also like to be able to go to higher energies, because at very high energies where these accelerators run out of steam, when it's really testing the acceleration process, the cutoffs are a characteristic field. One would like to have a wide field of view to be able to do surveys, improved angular resolution to really see whether these sources, these extended objects, have the fine structures which we see, for example, in X-rays. And we'd like to have higher detection rates to see such flaring AGNs. We can get the timescales maybe down to seconds, which would allow tests of quantum gravity at Planck scale. In fact, there's quite a bit of reserve in the technique. This plot shows you the angular resolution in arc minutes versus gamma ray energy, which can in principle be achieved with the technique if one looks at the limitations imposed by the shower development. Meaning, at a TV energy, one can go sub-arc minute in angular resolution, whereas current instruments have a couple of arc minutes, about a factor of 10 worse. So one can certainly, the technique has significant reserves to boost things. And the way it essentially works, oops, I hope this is visible, if you have a single telescope, you get a 300-meter light pool in which you detect the shower. Apologies that this is not very nicely visible. Now, if we have a 4-telescope system, then the really nice events, the sweet spot is the one where the light pools, where all the 4 telescopes can detect the shower, meaning the shower impact point is within 150 meters from each of the telescopes, and essentially this is the case in this corner of the array. And all the outside region give us reduced quality images. Now you see immediately, if you simply add more telescopes, you go from one such sweet spot to a sweet area, which is now significantly larger, and it's growing faster than the number of telescopes. And of course you can increase further the density and get additional images which provide improved background rejection and angular resolution. So that's sort of the idea behind CTA. It's basically essentially a brute force approach, saying one will deploy lots of telescopes, a large array to get milligraph sensitivity in the 10 GeV to 100 TeV domain by an array of about 50 to 100 telescopes. In addition, to expand the energy range, one could, in the center of this array, put a couple of bigger dishes, or just dense pack smaller dishes and couple them electronically. What's interesting, what we found is that these outer telescopes in this case are quite interesting because they sort of serve as a veto counter, which allow to reject cosmic rays, which mimic low energy gamma rays in the central region but leave traces in the outer telescopes. And then to go to very high energies, one needs to cover sort of 10 square kilometers. So the idea is to add another halo of telescopes around, extending a couple of kilometers out. Now this would be a rather flexible facility with this number of telescopes. You can either make a deep field with all telescopes looking at one way. You can split it up, look at a semi-deep field somewhere, monitor objects with a couple of telescopes, use a third of the telescopes to look at another source. So it's really a very flexible instrument. And of course, switch the telescopes such that their fields of view overlap and make surveys. This would allow one to survey the entire sky, not just the galaxy, within a year at a better sensitivity than what we have now. And it's not science fiction in the sense that the technology is there. We could essentially start building this thing today, taking, instead of 4, 100 HESS-1 telescopes, plus a handful of bigger telescopes, which we already have now. Just to illustrate the sizes of telescopes which exist in the world, this is a HESS-1 telescope, 100 square meter. The MAGIC telescope in Palma with about 230 or so square meter. And we have a HESS-2 telescope in construction in Namibia to go to low energies, increased sensitivity. This will be a 600 square meter dish, and it's coming along. I just used that opportunity to show it's coming along nicely. This is sort of the frame of this telescope, which is on a trial assembly here. And just to put the scale, there's a little truck hidden here behind. So it's really a fairly sizable object. Now we know that it works. We can do simulations of such an array, and we find that we get indeed milligraph sensitivity at TeV energies, and we do get sort of 30 GeV or so energies threshold. So that works. The problem is it is expensive, and with a target which we have, which is we believe we can maybe find about 100 million euro, it would not be possible to build this based on the current technology. So we need to really improve production techniques. We also need to improve instrument reliability. We also, in the meantime, believe that we can build quite a bit better telescopes. And finally, we need to learn how to operate these things as a sort of a public observatory like the X-ray observatories. So there's a significant effort required to optimize the design, and that's basically what's now moving ahead. There are questions like what kind of pixel size do you need to really image showers at the optimum quality. Of course, a high-resolution shower image is nice, but realize this image costs 16 times as much as this image, and the question is whether it has correspondingly more information. So the challenge for this new instrument is not to build sort of the best telescope you can build, but build the best system you can build, and to build the individual telescopes just such that the cost is reasonable. It does what it needs to do, but not more. And sometimes I like to use this image. What we try to find is the right balance. Obviously, you don't want this. This is sort of our current instruments. This is also a bit tricky. I mean, this is very fancy, high-tech, but it's very expensive, and you're using a lot of money on features which you never use. And it's not sort of the daily drive to work. So what we want is sort of a telescope which is the equivalent of something like this, which can be produced and operated reliably in large numbers. Well, I did show this at a German funding agency. I was criticized, so I also have a version with the German characters. Yes. Okay, so as I mentioned, there is a design study going on. We have quite a number of partners all across Europe. Very strong contributions from Germany, France, Italy, but a large number of countries involved, including Japan most recently, joined this project. And of course, we're still looking to get additional partners, and this is also one of the reasons I'm visiting here. Of course, it would be very interesting to have groups from Sweden with their experience, in particular in dark matter detection, join this project. As I said, we expect that there will be a large number of objects of the order of 1,000 or more detected. So this will not be run as a closed shop. It will be run as an open observatory, where an observer does a proposal and maybe a year later gets its data back and stuff is put on a virtual observatory. So this will really be run like a regular observatory. Now, where are we? The project was as an emerging facility on the S3 roadmap for future research infrastructures. We're just now trying to upgrade its status in the next iteration of this roadmap to a full project. We've been given very high priority in the Aspera roadmap, which gives the status and perspective of astroparticle physics in Europe. In the very near future, there will be a roadmap for AstroNet, which is the European astronomy community. And again, there we anticipate a very positive statement. So the hope is that over the next 3 or 4 years, we'll be able to really define the array and its science goals in an optimum way. And then maybe starting 2012, 2013, starting to implement this next generation instrument, which will hopefully get us another big step further. Thanks a lot.
Thank you for this nice talk. Any questions? Yeah.
Do you see any difference in the cutoff of the spectrum with high energies from different sources?
Oh yeah.
In particular, the remnants. I mean, there are lots of reasons why you should see it. Magnetic fields and size and age.
Yeah, we do see different cutoffs, and in fact, a little bit the worrisome thing is, you know, that there's the knee of cosmic rays at 10 to the 15, and all the remnants which we see seem to cut off earlier. So I mean, they cut off at, if you fit an exponential cutoff, 1713 cuts off at some, what is it, 20, 15, 20 TeV. Beta Junior cuts off at a couple of TeV. So we have not yet seen the sources which go all the way to sort of the knee.
Yeah, but you don't see any correlation with any other properties of the cutoff?
Well, unfortunately, I mean, this is one of the reasons we want to build CK. We don't have that many sources. I mean, right now, we have sort of 2 or 3 remnants where we see a cutoff, and it's very hard to correlate them. We have so these 24 pulsar nebula. We're just now trying to make a coherent effort to sort of understand the properties, but unfortunately, of course, the pulsar nebula also depends very much on the environment, which depends on which kind of supernova generated it and how the ambient density is. So it's, with these small samples, it's very hard to make sort of generic statements. That's what we find.
You mentioned that you could see some quantum gravity effect.
No, we could not. We are
No,
looking
but
for.
not even in principle.
In principle, we could, yes.
But I mean, you are 16 order of magnitude away from the Planck mass.
We are 16. This is right. But on the other hand, I mean, these sources are many hundreds of megaparsecs away. So particles propagate for 10 to the 8 years, and we're looking for differences in propagation speeds of the order of a couple of seconds. So that's basically where you gain the sensitivity.
You mentioned that the search for dark matter would also be a subject for CDA. Is there already a group in Hesse working on this subject?
There are groups in Hesse working on dark matter, in particular in France. We do have limits on dark matter right now from the Galactic Center. We have looked at a couple of dwarf galaxies. We're just doing right now an interesting analysis looking for intermediate mass black holes, but I don't think we've fully explored the subject. Should also say, I mean, Hesse currently has the problem that the energy threshold, which is 100 GeV, is for the conventional dark matter is a bit on the high side. This will hopefully improve with Hesse 2.
When will Hesse 2 finish?
Well, we hope 2009. And then we need to see, in principle, it could go down as low as 20 GeV. Question is what kind of signal to background we'll get at these energies. There's very little experience, and it turns out that the modeling of air showers and backgrounds seems to be not very reliable. So it's really something which one needs to learn.
More questions? Okay.
You mentioned these dark sources. The spectral shape from those, are they very similar or are they different in some way?
Well, they all look different. I mean, it would of course be nice if they had been all identical. You could say these are things like, as I said, intermediate mass black holes might be one possible candidates, but they're all different in shape, and they're all essentially different in spectral characteristics. So some of them are almost point-like. Some of them are most of them are extended. Spectral indices differ. They range from sort of 2.1, 2.2 to 2.7, 2.8. So they don't seem to be sort of one identical underlying mechanism. In a sense, like I mean, the thing which first comes to mind is sort of dark matter annihilation, maybe, but then they should all have identical spectra, and they definitely don't. Doesn't exclude that one of them is something